Assalamualaikum and hi. In this video, my groups and I will briefly explain about analytical instrument of gas chromatography. Before we start, these are the presenters. GC or gas chromatography is basically a term to describe the group of analytical separation techniques used to analyze volatile substances in the gas phase. In gas chromatography, the components of the sample are dissolved in a solvent and vaporized in order to separate the analytes by distributing the sample between two phases, a stationary phase and a mobile phase. The mobile phase is a chemically inert gas that serves to carry the molecule of the analyte through the heated column. Gas chromatography is one of the sole forms of chromatography that does not utilize the mobile phase for interacting with the analyte. A stationary phase is either a solid absorbent, termed gas solid chromatography (GSC), or a liquid on an inert support, termed gas liquid chromatography. Before we construct the instrument, there are four objectives that we want to achieve. 1. To determine the retention time of N-butanol and 2-propanol. 2. To identify the components present in a standard mixture based on the TR. 3. To identify the components present in an unknown sample. And lastly, to determine the effect of temperature on retention time and resolution.
Methodology of gas chromatography. As we can see here, this is a schematic diagram of gas chromatograph, which consists of gas flow regulator, carrier gas tank, sample, injector port, column which inside the oven, detector, waste and computer for data analysis. Okay, for this diagram, this is a block diagram of gas chromatograph, which show the flow of the gas chromatograph function. Okay, for the function of each component in gas chromatograph, firstly, carrier gas, which is mobile phase. In this carrier gas, there is inert gas, which is helium, nitrogen and hydrogen that transport the sample through the column. Next, sample injector, a heated pot where liquid or gas sample are introduced via a syringe through a rubber spectrum, immediately vaporizing the sample. Next, column, stationary phase, the heart of the GC, often a coiled capillary column, which is fused silica or a packed column placed within a temperature controlled oven. Next, oven. Oven control the column temperature to enable separation of components based on their boiling points and interaction with the stationary phase. Next, detector identifies and quantifies the separation components as they emerge from the column. For example, flame ionization detector (FID), thermal conductivity detector (TCD), and lastly, data system chromatogram. Chromatogram records the signal from the detector, producing peaks that represent components over time.
So as you can see here, this is the sample for 2-propanol at 70 degrees. So it was recorded that there are 3 peaks that was recorded, where the first peak is very high. So as you can see on the result, the retention time for the first peak is 2.706, while the percentage area is 99.97 and the height of the first peak is 2.35. Next, the second sample is N-butanol at 70 degrees. There are also 3 peaks, where the third one is a very high peak that was recorded. So let's look at the third peak. Its retention time is 5.973, while the percentage area is 99.73, and the height of the highest peak is 6,512.98. So this is the sample mixture for a third sample at 70 degrees. So as you can see that there are also three peaks, where the first peak was recorded the very highest one. The retention time is 2.671, while the percentage error is 38.17, and the height is 9,816.68. And the last peak was recorded the second highest peak, where the retention time is 5.827. The percentage area is 61.81, while the height is 4,753.16. So as you can see, this is the second sample mixture on 100 degrees. So there are also three peaks, where the first peak is the second highest of peak, while the third peak is the highest peak that was recorded. So as you can see, the rotation time for the highest peak on peak 3 is 3.280 in minute, while the percentage area is 61.68%, and the height of it was 1.2157 for exponent 4. And the second highest peak that recorded in retention time was 2.270 in minute, while the percentage area is 38.30%, and the height of it was 9,128.67. And the last sample is the sample mixture on 140 degrees. So as you can see, there are four peaks that was recorded, where the highest peak that was recorded was in the third peak, where the rotation time of the highest peak is 2.240 in minute, and the percentage error of it was 61.65%, and the height of it was 1.42665 exponent 4. And the second highest peak was recorded on this sample was the second peak, where the retention time in minute of it was 1.954, and the percentage area of it was 38.29%, and the height of it was 9,241.84. So, to explain the reasoning used to determine which peak in the unknown chromatogram correspond to each compound in the standard mixture, we have been concluded that the N-butanol are the reference for the unknown compound because of the chromatograph that has been out from the experiment result. So, as you can see, the retention time for N-butanol is 5.973, while the unknown is 5.971. The peak identification using retention time for these two compounds have extremely close, indicating that both compounds eluted at nearly the same time under the same chromatographic conditions. This shows that retention time alone may not always be sufficient to clearly distinguish between compounds, especially when their chemical properties are similar. However, because the N-butanol standard was analyzed separately, the peak with a retention time closest to 5.973 minutes was assigned as N-butanol, while the other peak was classified as the unknown compound. For the area percentage for N-butanol, it is 99.738, while the unknown is 99.687. These values are almost identical, suggesting that both components are present in very similar concentrations within the sample mixture. This indicates that the mixture contains comparable amounts of N-butanol and the unknown compound rather than one component being dominant over the other. While the height percentage of N-butanol is 6,512.90, while the unknown is 6,437.54. The slight difference between these values further supports that both compounds are present in nearly equal quantities. Since the retention times of N-butanol and the unknown compound differ by only 0.002 minutes, this suggests that their peaks are very closely eluting and may partially overlap. This highlights the importance of achieving complete peak separation, as overlapping peaks can lead to misidentification or inaccurate quantification. To improve resolution, changes such as modifying the column type or adjusting the temperature program could be applied in future analysis. So, based on the retention time comparison with the standard, one peak was identified as N-butanol, while other one as unknown compound. The nearly identical peak errors and heights indicate that both components are represented in similar concentrations in the mixture. However, due to extremely close retention times, further confirmation using methods such as GCs would be recommended for definitive identifications. To discuss the effects of reducing and increasing the column temperature on retention time and peak resolution, we have concluded that if the effect of increasing column temperature on retention time is increased, the analyte molecules gain more kinetic energy and interact less strongly with the stationary phase. As a result, compounds travel through the column more quickly, leading to shorter retention times. In practice, this means peaks appear early on the chromatograph, which shortens the total analysis time. However, when temperature is too high, compounds may elute too rapidly, causing peaks to become narrower and close together, which can reduce separation efficiency. But if the column temperature on retention time decrease, the compounds interact more strongly with the stationary phase and move more slowly through the column. This leads to longer retention times, meaning peaks appear later in the chromatograph. Lower temperatures can improve separation between closely relating compounds because the increased interaction time enhances the differences in retention behavior. However, excessively low temperatures can cause peaks to broaden, resulting in longer run times and reduced peak sharpness. Other than that, for the column temperature on peak resolution, if the effect is increased, the peak resolution often decreases as well because compounds elute close together. This is especially problematic for compounds with similar boiling points or polarity as their retention behaviors become more similar at elevated temperatures, increasing the risk of overlapping peaks. While if the column temperature on peak resolution decreases, it will generally improve peak resolution because compounds spend more time interacting with the stationary phase, allowing subtle differences in their chemical properties to become more pronounced. This results in better separation between peaks, although at the cost of longer analysis times.
Conclusion: this experiment demonstrated the use of gas chromatography to separate and identify alcohol samples by comparing their retention times with a standard mixture. Repeated injection of the standard mixture at the beginning, middle, and end of the analysis produced consistent chromatograms, confirming that the instrument was operating reliably throughout the experiment. The N-butanol sample showed a single peak with a longer retention time, while the N-propanol sample showed a single peak with a shorter retention time. These difference in retention times are related to the volatility and molecular structure of the compounds. By comparing the chromatograms of the sample with the standard mixture, both N-butanol and 2-propanol were successfully identified. Overall, the experiment achieved its objective and confirmed that gas chromatography is an effective and reliable technique for the analysis of volatile organic compounds.